We used to only know about the planets that circled around our sun, but now we know that there are rocky worlds and huge gas clouds that circle other stars. They have a great story to tell. The early history of these planets would have been very, very violent. Planets are made the same way everywhere. They come from the dust and other things that are left over after stars are born. So if they're all made the same way, what makes them so different? As it turns out, the universe is full of galaxies, gas clouds, stars, and planets. There are 8 worlds in our sun's system. But now we know that they are just a small part of the huge family of planets in the sky. It's a very important moment in the history of science, to be sure that there are other systems of planets out there. And in our Milky Way galaxy, which contains an estimated 100 to 400 billion stars, there are likely 100 to 400 billion planets, as nearly every star may host at least one planet on average. NASA launched the Kepler Space Telescope in 2009 to find planets orbiting other stars. By the end of its mission in 2018, Kepler confirmed over 2,600 exoplanets, with thousands more candidates identified. Some are massive gas giants, larger than Jupiter, often called hot Jupiters. Others are rocky super-Earths, or mini-Neptunes, with sizes up to about twice that of Earth, though larger planets often have thick, gaseous atmospheres rather than rocky surfaces. Some follow tight, eccentric orbits so close to their stars that they experience extreme temperatures often exceeding 1,000 degrees Celsius. One thing is clear, no 2 planets are the same. Each one is unique, but most of these new worlds are very far away and hard to study. Most of what we know about how planets work comes from the 8 that circle our sun. There are 2 main kinds of planets that we live on. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 worlds is very different from the other 7. When our solar system was born, 4.6 billion years ago, they started to develop their own personalities. When the sun ignited, it released a massive cloud of gas and dust into space. All 8 planets, including the metal planets closer to the sun and the gas planets farther away, came from this cloud of space debris. All of the worlds in our solar system are made of the same materials. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed close to the sun, where it was much hotter, and some formed far away, where it was much colder. And since the situations were so different, the things that came out of them were also different. So at the beginning of the solar system, there was a pretty even mix of silicates, water, vapor, hydrogen, a lot of hydrogen, methane, and other things. These elements in the dust cloud are like ingredients in a cake. They cook in different ways based on how the ingredients are mixed and how hot the oven is. And you'd mix the ingredients just like you did with the cake. Then you'd put it in the oven and bake it, and it would change. So basically, this is what happened in the solar system. Overall, the planet cooks in a slightly different way depending on how close it is to the sun. Near the sun, where it is hot, gases are burned off and water boiled away. Only materials that stay solid at high temperatures like metals and rocks can survive. This is why only rocky planets form close to the sun. As a planet moves farther away from the sun, it cooks in a different way. But what kind of planets will form depends on what's in the cloud. Based on what kind of cloud a solar system forms in it might not have any rocky planets because it didn't have enough materials to make something like Earth. Instead, it might have more gas giants, and none at all. If you want planets that are made of rock, you need a cloud full of metals and rocks. The next step is to turn down the heat. As it cools, some of the things in it that have a high boiling point start to condense out as solids. And these very small mineral grains can start to form. These tiny pieces of rock and minerals are the beginnings of a new rocky world. They start to stick together over time. If you had one dust molecule and another dust molecule, and they would basically hit each other and make one slightly bigger dust molecule, and they'd keep getting more and more. This process is called accretion. As these things got bigger, they became basically rocks. Then rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders. At some point, you'll have something big enough that its weight is strong enough to start pulling things towards it. So instead of just crashing into things and getting bigger that way, it was actively pulling things in. At first, there were a lot of young planets in our own solar system, maybe 100. Most of them didn't make it. If you go to the asteroid belt and look at the asteroid 4 Vesta, you can get a good idea of how big a hard planet has to be before it can pull itself into a sphere shape. Vesta, at about 329 miles across, is not quite spherical. A growing planet typically needs to be around 500 miles in diameter to achieve hydrostatic equilibrium and become spherical, though this depends on its composition. Then it has enough gravity to crush it into a sphere. Any smaller, and it stays an irregular shape. Every time a round baby planet crashes into something, it makes it hotter and hotter until it starts to melt. Gravity is now starting to sort the heavy things from the lighter ones. Lighter things tend to float up and form a crusty layer, while heavy things like most metals fall down and form a much denser core at the planet's center. Finally, the young planets are starting to look like planets. But now they have to make it through a time of violence and destruction, a cruel time that will decide which planets will live and which will die. After the sun was made, all 8 of our planets came from the same cloud of dust and gas, but they turned out to be very different. There was no real plan for how each of the new planets should be made. They did follow the rules of physics and chemistry, but most of what happened was just a matter of luck. About 4.5 billion years ago, our sun was surrounded by about 100 young planets. It turned into a demolition derby. Planet hit planet. Most were wiped out. The early history of these planets would have been very, very violent, with many of these collisions happening in the last stages of each planet's growth. As these collisions happened, and things ran into each other, some of the planetesimals started to grow at the expense of the others. And these things that would eventually become planets grew and grew. As they got bigger, they sucked up all the smaller planetesimals around them, which caused a lot of space debris to hit the surface of the protoplanet. After it was over, there were only 4 different rocky planets left. Because of the things that happened to each planet in the past, they are all so different from each other. Mars is a frozen wasteland. Earth flows with liquid water. Venus is a place full of volcanoes. And Mercury is small, empty, and very hot because of a huge crash. Mercury, for example, has a very thin crust and is very dense, so it could have been a bigger planet in the past. Then something hit it at an angle, which tore off the lighter crust and left only the dense center. Also hit hard was the young Earth. At the end of the Earth's development, it was hit by something else which tore apart its mantle and sent the pieces into orbit around the Earth, where they regathered to form the Moon. Something also seems to have crashed into Mars. The crust of the Earth is thinner in the north than in the south. One idea about what might have caused this is that the northern hemisphere of Mars was hit by something early in the planet's history, which blew off a lot of its crust. And that crust started to build up again in the south of Mars. There were 2 effects of all these collisions. They cut down on the number of baby planets that were still alive, and they brought more ingredients to the survivors. If you had a collision with something that was metal-rich, those chunks would tend to descend down into what was becoming the core, where if you collided with something light or icy, they would tend to just float about and form part of the crust instead. Near the Sun, there were 4 rocky planets that were almost done. They were made of a solid core of hot iron, surrounded by a layer of liquid iron and a shell of molten rock. On top of that is a crust on the surface. All of these rocky planets were made the same way from the same basic materials. But they were all very different. They were all different sizes and had very different plans. It may look like space is empty, but it's not. It's full of things that came from the sun. Strong magnetic fields are made by the sun. These fields rise up in giant loops above the surface. When they hit each other, a storm of very hot, very charged particles shoots out into space. The name for it is the solar wind. Astronauts can see it from space, but only when they close their eyes. When you close your eyes, you sometimes see a little flash. And that flash of light is caused by an energetic particle going through your head and interacting with the fluid in your eye. And you see one of these every few minutes. Solar wind could kill the astronauts if they were exposed to a lot more of it. During the Apollo program, there was an explosion on the sun between two moon missions that would have killed the astronauts if they were there. So radiation in space is a big deal. But here on Earth, the solar wind doesn't pose much of a threat because we are protected by an invisible magnetic field that comes from the center of the Earth. You can make magnetic fields from motion by converting the energy of the motion into magnetic energy. Deep inside the Earth, the same thing happens. As the Earth spins, the hot liquid metal flows around the solid core, turning its energy into a magnetic field that comes out of the poles. It keeps the solar wind from getting into the atmosphere of the planet. And if the planet has a magnetic field, the magnetic field will send the solar wind around the planet. The solar wind is pushed away from Earth by the magnetic field, which protects the atmosphere and everything on the surface. Big storms of solar radiation can sometimes mix up the magnetic field. Then big light shows called auroras happen over the poles. Without a magnetic force field, Earth's atmosphere and water would be blown away by the solar wind, leaving a planet that is dead and dry, a lot like Mars. Mars was made the same way Earth was, but today it's cold and dry, and there's not much going on. So why have the two planets changed so much? NASA sent 2 robots to Mars in 2004 to find out what was there. The Spirit and Opportunity rovers looked at miles of the surface of Mars. They proved that Mars is a dry, dangerous desert with only 1% the atmosphere of Earth. But they did find signs that water used to be there. Mars wasn't always a dry, barren place. We have found strong evidence that water was once below the surface, rose to the surface, and evaporated away. In a few places, we can also see ripples that are made when water flows over sand. So not only was there water under the ground, it had flowed across the surface. If Mars used to have water, it probably also had a lot of atmosphere around it. So what happened? We can see that there were volcanoes on Mars in the past. So it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core surrounded by liquid metal in the middle. It should have also had a magnetic field. The question is, where did it go? Early in the planet's history, Mars apparently had a strong magnetic field. And it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. Because of this, it will lose heat more quickly. And that means that a liquid core can become solid when it freezes. If you completely freeze the core, the convection will stop. The flow stops, and the magnetic field disappears. As soon as the magnetic shield stopped working, the solar wind blew away the atmosphere, and the water evaporated. Mars turned into a cold, empty place. The rocky planets, Mars, Earth, Venus, and Mercury, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. These monsters are very big, made of gas, and have no solid surfaces at all. So far, astronomers have found more than 400 new planets in solar systems far away. Almost every one of them is huge and made of gas. Our solar system has 4 of these so-called gas giants: Jupiter, Saturn, Uranus, Neptune, all of which have thick, soupy atmospheres with lots of hydrogen, helium, and methane. Why are these outer 4 made of gas when the inner ones are rocky? It's very cold here, 500 million miles from the Sun. At the start of the solar system, there was some dust, but mostly gas and water frozen in ice grains. It was cold enough to make solid snow where the big planets began to form. And we think that we were able to make ice snowflakes, and that these were able to stick together to form the cores of the giant planets. We think that's why the big planets might have grown so big. Because there was so much ice and gas, their cores grew to be about 10 times the size of Earth. A lot of gravity came from these big cores. They had so much pull that they sucked in all the gas around them and made thick, soupy atmospheres that went down tens of thousands of miles. The more gravity they made, the bigger they got. More and more dust and debris kept getting pulled towards the planets, and this is what made up their moons. Each of Jupiter and Saturn has more than 60 moons. The gas planets have something else that makes them unique: rings. Saturn is different from the other planets because it has these beautiful rings. It turns out that Jupiter, Uranus, and Neptune also have rings, but they are very weak and hard to find. But they are there. There are rings around all 4 of the gas giants, but Saturn's are the most obvious. From far away, Saturn's rings look like a single flat disk, but in reality they are made up of thousands of small rings that are only a few miles wide each. When the Cassini probe flew by, it found that billions of pieces of ice and space debris were moving around inside the rings at up to 50,000 miles per hour. These pieces of ice and rock hit each other all the time. Some of them turn into small moons. Some of them fall apart. But they never grow bigger because Saturn's huge gravity pulls them apart. Scientists are just now starting to figure out how the rings came to be. The idea is that a comet hit a moon and knocked it out of its orbit, bringing it closer to the planet. Saturn's gravity tore it to pieces. All of that stuff got stuck in rings that went around the planet. But the real mysteries of the gas giants are deep inside them, tens of thousands of miles below the clouds. Here is where things really get going. It's a place so extreme that it goes against the natural laws. Most of the new planets we find orbiting faraway stars are huge gas planets. They are so big that Jupiter seems small next to them. But nobody knows what happens inside gas giant planets, whether they are in our solar system or far away. We know that Jupiter's thick atmosphere goes down 40,000 miles, and we can see bands of gas moving at high speeds that make violent storms on its surface. But we don't know what's happening inside far below the storms. NASA sent the Galileo spacecraft on a 14-year trip to Jupiter to find out. December 7, 1995. Galileo sent a probe into Jupiter's atmosphere, which it did at a speed of 160,000 miles per hour. As it fell through the thick air, the parachutes slowed it down. It saw lightning in the clouds and 450-mile-per-hour winds. The probe transmitted data back to Earth for 58 minutes. What happened to the Galileo probe that we dropped in? It didn't hit anything. It just kept falling into Jupiter's environment, and the pressure kept going up and up and up. As it fell, it measured pressures 23 times higher than on Earth and temperatures over 300 degrees higher than on Earth. When you're in the environment of a gas giant and you go deeper and deeper into this soup of hydrogen, which has no solid surface, it can still be very heavy. And so eventually you would be crushed by the overlying weight of the material that's there. Even though the probe only went 124 miles down before it was crushed, it showed scientists what Jupiter's inside looked like. But the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. Jupiter's magnetic field is 20,000 times stronger than Earth's, and so big that it goes all the way to Saturn, which is more than 400 million miles away. Like on Earth, Jupiter's magnetic field keeps the solar wind away from the atmosphere and keeps it safe. When scientists looked at Jupiter's magnetic field, they found that it affected the moons of Jupiter. The volcanic moon Io orbits only 217,000 miles from the planet. Every second, Io's volcanoes send a ton of gas and dust into space. It gets even stronger because of Jupiter's magnetic field, which makes powerful belts of radiation. And this makes the area around Jupiter very busy in a lot of ways. If you point a radio antenna at Jupiter, you can hear how the planets and the magnetic field interact with each other. Jupiter and Saturn can make auroras without the solar wind. They make their own magnetic fields because they are so big. These auroras show that planets with gas also have magnetic fields. But how do magnetic fields get made on gas planets? On Earth, the job is done by a very hot liquid metal that spins around the planet's solid iron core. Gas giants like Jupiter generate magnetic fields through metallic hydrogen in their cores, which conducts electricity under extreme pressure unlike the hot liquid iron cores of rocky planets. They initially formed around cores of dust and ice, so we don't really know what's going on inside. We really don't know what makes up the deepest parts of Jupiter's interior, so it's possible that Jupiter has a solid core at its center, or it could just still be liquid. We might never know. No probe could ever go the 44,000 miles to the center of the planet to look into it. Galileo was destroyed before it could reach the center of the planet. Gravity and heat shape how planets evolve from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's one more thing that has a big effect on how planets turn out, and that ingredient is water. Planets may look like they are fixed and don't change, but they are always changing. One planet in our solar system lost its atmosphere and turned into a desert. Another planet got too hot and changed into the planet from hell. Planet Earth has also changed, and it was water that changed the game. When you look at Earth from space, you can see a lot of water. We are, after all, the blue planet. That means it must be very wet, right? At first glance, our world seems to have a lot of water. After all, 3/4 of it is made up of oceans. Not true. Only 0.06% of the mass of the Earth is water. Some water is on the surface as oceans, and some is stuck in the mantle. But actually, the Earth is a relatively dry rock. All of the inner rocky planets formed very close to the Sun, so they started off dry. Any water they might have had either evaporated or was blown away when things hit. These massive collisions that formed the Earth were so energetic that if there had been water here, it would have evaporated and left the Earth. So where did all the new water on Earth come from? It's now here. When you look at Jupiter, Saturn, Uranus, and Neptune, you can see that they have a lot of water locked up inside them. And even more dramatically are the moons. At least half of the water on the moons of Jupiter, Saturn, Uranus, and Neptune. A lot of water was out there. So how did some of it get to planet Earth? And the answer is almost certainly that there were some asteroids and comets left in our solar system that were far enough from the Sun that they could keep their water. There were millions of these watery asteroids and comets that flew into the inner solar system. Some of them crashed into our planet. Over time, the Earth got the water that used to be in the asteroids. This is what makes up the mass of water that now covers almost all of the Earth. Without surface water, there would have been no life. What about water that is too much? The oceans would be much deeper and cover the continents and even Mount Everest. And it's likely that the exact amount of water that the Earth has is what made it possible for us Homo sapiens to evolve into a technological species. About 4 billion years ago, a blizzard of comets and asteroids brought just the right amount of water to Earth. This is how the world we know today came to be. And it's possible that the same thing is going on somewhere else in the universe right now. There is a lot of water out there that much is certain. The most common atom in the universe is hydrogen, and oxygen is one of the next most common. H2O will definitely be a very popular molecule, which is exactly what is happening in our universe. So water is everywhere in the universe, and we're finding that planets are too. While no exoplanet with confirmed liquid water has been found, missions like the James Webb Space Telescope are studying planets' inhabitable zones to detect signs of water. As of 2025, scientists have confirmed over 5,700 exoplanets using missions like Kepler, TESS, and ground-based observatories. Our world doesn't look like any of them. Scientists have found Earth-sized planets in the habitable zones of their stars, such as those in the TRAPPIST-1 system. But we have not yet confirmed a planet with Earth's exact size, mass, chemical makeup, and surface conditions such as liquid water and an oxygen-rich atmosphere. So it remains an extraordinary holy grail for humanity to find other abodes that remind us of home. But we'll keep looking. Our galaxy contains an estimated 100 to 400 billion stars, and most, if not all, are likely to host at least one planet, suggesting 100 to 400 billion planets in the Milky Way. We still hope that when we find planets like Earth, It will help us a lot to understand how the planets in our solar system and Earth evolved compared to the planets in the outer solar system. We are entering what will be called the golden age of planetary exploration in the future. We'll start to really understand for the first time how different things are out there. I think this is going to be a very exciting time. The laws of physics and chemistry tell us how planets are made. Many scientists think it's only a matter of time before we find another planet like Earth, one that formed from the same materials in the right place with the right amount of water. One thing is certain: there are billions of planets out there waiting to be discovered. Forget everything you thought you knew about the universe. What if a telescope found a signal that could mean life or a galaxy that shouldn't exist? We're not dreaming anymore. The James Webb Space Telescope is rewriting the rules. It's not just looking at stars. It's staring into the past, pulling up data that makes scientists question everything. Galaxies forming before they had time. Planets with chemicals that scream life. Structures too perfect for a chaotic cosmos. This isn't science fiction. It's real, measurable, and it's shaking our understanding to the core. The universe isn't playing by our playbook. It's showing us a cosmic puzzle, and the pieces don't fit. Webb's infrared eyes are catching things we can't ignore. From signals 124 light-years away to galaxies born when the universe was a baby. We're not just finding answers. We're finding questions we didn't know to ask. Today, we're diving into 4 discoveries that turn it all upside down. A planet with a gas that might mean life. A spiral galaxy that looks like home way too early. Auroras on Neptune that don't add up. And galaxies so old they break the timeline. This is the universe talking. And it's not whispering. It's shouting. Stick with us to see what Webb found and why it changes everything. What if a planet 124 light-years away is breathing? The James Webb Telescope found something on K2-18b that's hard to explain. K2-18b isn't just another dot in the sky. It's an exoplanet orbiting a dim red dwarf, sitting in the sweet spot where water could stay liquid. For years, it was just interesting. Too big to be like Earth, too far to make headlines. Then Webb turned its mirror, and everything changed. It scanned the planet's atmosphere, sifting light for chemical clues. What it found stopped scientists cold: dimethyl sulfide. On Earth, this gas comes from life. Tiny ocean creatures like plankton pump it out when they die. It's the smell of salty sea air, sharp and fleeting. Sunlight burns it away fast, so it needs constant replenishing. By life, Webb caught this signal in K2-18b's skies. Not a whisper, but a shout. The levels were high, way higher than Earth's. Think of it like spotting smoke from a fire across the galaxy. You don't know what's burning, but something's alive. This planet has a thick, hydrogen-rich atmosphere, probably cloaking a deep ocean. If life's there, it's not fish or forests. Maybe microbes floating in that alien sea churning chemicals, or something we can't even picture. The signal's strong enough to suggest more than a few specks. It could be an ecosystem, a living world pumping gas on a massive scale. But hold on, science doesn't jump to aliens. There's a catch. Other chemicals like methane can mimic this signal in infrared. Mistakes happen, so they checked again. The signal didn't fade. It got clearer. Stronger, estimated at 1,000 times Earth's levels. That's not a glitch. That's something real. Now, could it be geology, a weird volcano, or gas pocket? Maybe. But on Earth, nothing non-living makes dimethyl sulfide like this. We've looked. No dice. If K2-18b's doing it without life, we need a new rulebook. This is where the cosmic puzzle gets wild. K2-18b isn't some distant theory. It's 124 light-years away, close enough to study, far enough to haunt us. If this is life, we're not talking fossils or dreams. We're talking something alive right now, leaving its mark in the sky. Webb's data is solid, but it's not the final word. More checks are coming. Other telescopes, other teams. They'll rule out every trick, every false alarm. Chemistry, physics. If nothing else fits, we're left with one answer: life. That changes everything. We're not just asking if we're alone. We're measuring what else is out there. What's its chemistry? How does it survive? Is it like us or something stranger? K218b's signal is a piece of the puzzle, and it's screaming for attention. We used to think alien life was a future problem, something for starships or science fiction. But now it might be staring us down. A signal from a planet we can almost touch. This isn't the end of the story. It's the start. K218b's signal hints at life. But what if the universe built galaxies too perfect for its own rules? What if a galaxy looked like home, but showed up billions of years too early? Webb found one, and it's turning our timeline upside down. Meet Xulong, or Torch Dragon, a spiral galaxy spotted by the James Webb Telescope. It's not just far away. It's far back, shining from when the universe was barely a billion years old. That's not long after the Big Bang, when everything was supposed to be a mess. Picture the early cosmos like a stormy sea with gas and stars crashing, merging, tearing apart. Galaxies back then should be chaotic blobs, not orderly spirals like our Milky Way. Spirals need time. Time for gravity to settle, for stars to align into neat arms, for a disk to spin steady. That takes billions of years, or so we thought. Xulong breaks the rules. It's got those arms that balance that structure. It looks like it's been chilling for ages, not freshly born in a cosmic riot. Think of it like finding a polished statue in a quarry where rocks are still being blasted. It shouldn't be there, but Webb's infrared eyes caught it clear as day. The light we're seeing left Xulong when the universe was a toddler, yet it's already grown up. Its spiral arms are tight, its core is bright, and it's stable. That means it formed even earlier, maybe just a few 100 million years after the Big Bang. Here's the science. We measure this distance with redshift. It's how light stretches as the universe expands, pushing starlight to redder colors. Xulong's redshift puts it at 12.5 billion years away. That's not just a number, it's a problem. Our models say spirals come late after messy galaxies collide and cool. Xulong says otherwise. It's not alone either. Webb's finding more like it, galaxies too neat for their time. This is another piece of the cosmic puzzle, and it's not fitting. Why does this matter? If spirals formed this fast, the universe was cooking way sooner than we thought. Maybe gravity worked harder back then. Maybe dark matter, that invisible glue, pulled stars together like a magnet on steroids. Or maybe our whole timeline's off. Some scientists are rethinking how gas clumped in the early days. Others wonder if the first stars burned out faster, spitting out material for galaxies like Xulong. The wilder idea: the universe's rules might have been different back then. Not by much, but enough to rush things. This isn't just about one galaxy. It's about what's possible. Spirals like Xulong are stable. They're the kind of places where stars last, where planets form, where life might get a shot. If they were around this early, life-friendly, spots could have popped up way before we expected. That's big. It means our Milky Way, our home, isn't so special. It's just one of many, maybe late to the party. Xulong's telling us the universe didn't waste time. It was building homes while we thought it was still setting up shop. Webb's not done. It keeps spotting these early spirals, each one a jab at what we thought we knew. Xulong's not an outlier. It's a clue. A clue that the cosmic puzzle has more pieces than we guessed. We're not just looking at a galaxy, we're looking at a universe that's been ahead of us from the start. And that's what makes this so unsettling. The past looks too much like now. Xulong's early spiral defies the stars, but what's hiding closer in our own cosmic backyard? The James Webb Telescope turned to Neptune, and it's not what we expected. Neptune's the loner of our solar system. Far out, cold, dark, and barely studied. Most of what we know comes from one quick visit by Voyager 2 in 1989. Since then, it's been blurry glimpses through ground telescopes. Nobody thought to point Webb, our deep space champion, at a planet next door, but they did. And what it saw wasn't just pretty lights. It was a puzzle piece that doesn't fit. Webb caught Neptune's auroras glowing at its poles, not like Earth's northern lights, all soft and shimmery. These are wild, chaotic, driven by forces we don't fully get. Think of it like finding a strange signal on a radio you thought was broken. Something's broadcasting and it's loud. Webb's infrared vision cut through Neptune's haze, mapping heat and chemistry in ways we've never seen. It spotted auroras pulsing with weird patterns, hot spots where there shouldn't be heat, cold patches that defy the sun's weak grip out there. On Earth, auroras come from solar wind-charged particles slamming into our magnetic field. Neptune's got a field too, but it's a mess. Tilted, lopsided, nothing like ours. Those particles take forever to reach it, crawling through space from the sun. Yet Webb saw something else. Temperature swings that don't add up. Some areas cooled too fast. Others burned hotter than they should. It's like Neptune's cooking its own weather and we don't know the recipe. Here's the data. Webb's instruments tuned for distant galaxies picked up chemical shifts in Neptune's atmosphere. Methane absorbs light in weird ways, but something's tweaking it. Maybe magnetic storms. Maybe reactions we haven't pinned down. The auroras aren't just a light show. They're clues to a planet we thought we knew. Neptune's magnetic field is a beast twisting in ways that mess with our models. Those hotspots could be energy leaking from inside the planet. Those cold zones, maybe gas sinking in ways we didn't expect. We're not sure. And that's the point. Webb didn't just snap a picture. It raised questions we weren't asking. This isn't about some far-off star. It's right here in our own system. Neptune's been out there keeping quiet while we chased galaxies. Now Webb's showing us we missed something. The sample mentioned Voyager's flyby, but Webb's look is sharper, deeper. It's not just auroras. It's a planet acting alive with storms and heat and chemistry that don't play by our rules. And it's not alone. Uranus-Neptune's twin might be hiding similar tricks. We haven't looked hard enough. Our outer planets are strangers, and Webb's proving it. Why does this matter? It's another crack in the cosmic puzzle. We thought we had our solar system figured out. Earth, Mars, Jupiter done. But Neptune's saying, hold up. There's more. Its auroras hint at forces magnetic, chemical, maybe even geological, that could teach us how planets work. Not just here, but everywhere. If we're wrong about Neptune, what else are we missing? Moons with oceans. Weather we can't predict. This isn't just a pretty view. It's a wake-up call. The universe doesn't stop surprising us even in our own backyard. Webb's not done with Neptune. More observations are coming. Maybe they'll crack the code on those auroras, or maybe they'll dig up new mysteries. Either way, this telescope's rewriting what we thought was settled. It's telling us to look closer, even at the places we thought we knew. Neptune's auroras aren't just lights. They're a signal. Something's going on out there and we're just starting to listen. Neptune's auroras glow with secrets. But what if galaxies formed before they were allowed? The James Webb Telescope found some, and they're breaking every rule. Say hello to JD's GS Z14-0. It's not just a galaxy, it's a time bomb. Webb spotted it shining when the universe was only 280 million years old. Back then, the cosmos was a hot mess. Gas, swirling stars, barely sparking matter, still figuring itself out. Galaxies weren't supposed to happen yet. They need time. Time for gas to cool, for stars to clump, for gravity to sculpt something solid. Picture it like trying to bake a cake in a microwave that's still warming up. You shouldn't get a cake. But JD's GS Z14-0 is no raw batter. It's a full-on galaxy compact, bright, packed with millions of stars. This is nuts. Our models said galaxies take billions of years to get their act together. First you need stars. Tiny ones made of hydrogen and helium burning fast and dying young. They explode, spitting out heavier stuff like carbon. That stuff cools, collapses, forms new stars, and slowly builds galaxies. JD's GS Z14-0 laughs at that. It's got structure, mass, and shine all before the universe even had a chance to stretch its legs. Think of it like finding a skyscraper built before the invention of steel. Webb's got the receipts. It measures this with redshift. JD's GS Z14-0's redshift screams 13.5 billion years old. That's not just far, it's impossible. Or it was. This galaxy's got a mass of 100 million suns squeezed into 500 light-years. It's small but mighty, and it's not alone. Webb's finding more like it galaxies popping up way too early, too bright, too big. This is where the cosmic puzzle cracks open. Something sped things up. Maybe dark matter, that invisible scaffolding, yanked matter together like a cosmic tow truck. Maybe the first stars were giants blowing up fast and seeding galaxies in a hurry. Or maybe the universe's early rules were looser, gravity stronger, time weirder. Scientists are scrambling. Some say gas clouds collapsed faster than we thought. Others think dark matter played a bigger role. The wild ones, they're whispering about new physics stuff we haven't dreamed up yet. Why is this a big deal? These early galaxies aren't just old, they're game changers. If they formed this fast, the universe was ready for business way sooner than we planned. Stable galaxies mean stable stars. Stable stars mean planets. Planets mean chances for life way back when we thought the cosmos was still in diapers. Jada's GS Z14-0 isn't just a pretty dot. It's a clue that the universe didn't wait around. It was building fast while we were busy writing rules it doesn't follow. Webb's stacking up these finds, more early galaxies, each one a jab at our timeline. They're not flukes, they're a pattern. The cosmic puzzle keeps growing, and this piece is heavy. It's telling us the universe was never slow. It was always in a rush, spinning out galaxies like it had somewhere to be. And that's what's spooky. We thought we knew the story of the cosmos. But Jada's GS Z14-0 says we're reading the wrong book. Webb's not just showing us stars, it's showing us how much we've got to learn. Early galaxies flipped the script. But what does it all mean for us? The James Webb telescopes rewriting our place in the cosmos. Look at what we found. K218b's got a gas that might mean life pumping out signals we can't ignore. J-Long's spiral showed up way too early, looking like home, before it should. Neptune's auroras are dancing with secrets right in our backyard. And JD's GS Z14-0, that galaxy born too soon, says the universe was in a hurry. These aren't just dots in the sky. They're pieces of a cosmic puzzle, and they're telling us something big. The universe isn't what we thought. It's not slow, not empty, not quiet. It's been busy building galaxies, maybe even life, long before we had a clue. This changes the game. We used to ask if we're alone. Now we're asking how many others are out there. Are we just one piece in a massive puzzle or something special? Webb's data doesn't shout answers. It whispers hints. Galaxies too old. Signals too strong. Lights too weird. Each one's a crack in what we thought we knew. And it's not over. More discoveries are coming. More questions. More pieces. So what now? Keep looking up. The universe is talking, and we're finally listening. Not with dreams, but with hard data. Webb's showing us a cosmos that's alive, restless, and full of surprises. Are we ready to find out what's next? The puzzle's not solved. It's just getting started. We inhabit a galaxy known as the Milky Way, which contains hundreds of billions of stars. How did we arrive at this point, and what is our future? These concerns involve galaxies in every aspect. The known universe contains 200 billion galaxies, each of which is unique, immense, and dynamic. Where do galaxies come from? How do they work? What is their future, and how will they die? This is the Milky Way, our galaxy. Approximately 12 billion years old, the galaxy is a vast disk with enormous spiral arms and a central nucleus. It is only one of countless galaxies in the universe. Galaxies are massive assemblages of stars, first and foremost. A typical galaxy could contain 100 billion stars. They are actually stellar nurseries, the locations where stars are formed and perish. The stars in a galaxy are formed in nebulas, which are concentrations of dust and gas. Our galaxy contains billions of stars, many of which have planets and moons orbiting them. But for a very long time, we knew very little about galaxies. A century ago, we believed that the Milky Way was the only galaxy in the universe. In 1924, astronomer Edwin Hubble altered the entire situation. Hubble observed the universe using the most sophisticated telescope available at the time, the 100-inch Hooker on Mount Wilson near Los Angeles. Far, far away, he saw hazy masses of light in the darkness of the night sky. He realized they were not even separate stars. They were entire star-filled cities, constellations far beyond the Milky Way. The astronomers received an existential jolt. We went from the Milky Way galaxy being the only galaxy in the universe to billions of galaxies in a single year. Hubble made one of the finest discoveries in the history of astronomy when he discovered that the universe contains a large number of galaxies rather than just one. This is the Whirlpool Galaxy. It comprises over 160 million stars and is characterized by two enormous spiral arms. In addition, the stars of the huge elliptical galaxy M87 shine with a golden hue, since it is one of the oldest galaxies in the cosmos. And this is the Sombrero Galaxy. Its massive bright core is surrounded by a cloud of gas and dust. All galaxies are very beautiful. They stand in for the fundamental building block of the cosmos. As they spin across space, they resemble enormous pinwheels. Galaxies are enormous on a grand scale. Here on planet Earth, we use miles as our standard unit of measurement for long-distance travel. Astronomers measure distances in light years. This is how far light can travel in a year. Just about 6 trillion kilometers. Our galaxy's diameter is over 100,000 light years, and we're now located at a distance of 25,000 from its center. However, in the grand scheme of things, even it seems like a tiny dot. While the Milky Way seems enormous from Earth when compared to other galaxies, it is really rather little. Andromeda, the galaxy closest to us, is about 200,000 light-years wide, making it twice as large as the Milky Way. In our local universe, M87 dwarfs even Andromeda as the biggest elliptical galaxy. With a diameter of 6 million light-years, IC 1011 is the largest galaxy ever discovered. It's 60 times the size of our own Milky Way. It's common knowledge that galaxies are enormous and ubiquitous, but why is this the case? The origin of galaxies is a key mystery in astrophysics. Approximately 13.8 billion years ago, the universe began with what we refer to as the Big Bang, a period of intense heat and density. We know that there could not have been anything like a galaxy at that time. So galaxies must have come from that very early universe and formed from it. For stars to form and for galaxies to form from those stars, gravity is essential. After the Big Bang, the first stars began to emerge only 200 million years later. The earliest galaxies formed as their masses began to clump together because to gravity. Thanks to the Hubble Space Telescope, we can now see the early universe when galaxies were just beginning to form. Numerous galaxies are visible to the Hubble. The light we see from distant galaxies now, however, really departed those objects many millions or perhaps billions of years ago. What we see now is the distant past of those galaxies, since it took so long for their light to get to us. The Hubble Deep Field reveals a collection of fuzzy dots. They are quite different from the galaxies we see now. We can hardly make out these little specks of light. Those fuzzy patches of light are really millions or billions of stars beginning to combine. The oldest galaxies are represented by these barely visible blotches. They began to take shape around 1 billion years after the Big Bang. However, Hubble's range of visibility ends there. A second sort of telescope, one too large to send into space, is required if we are to travel much farther back in time. Not only can the telescope identify primordial galaxies, but it can also trace their evolution. The evolution of galaxy and galaxy cluster formation may be followed. All the galaxies that have developed since the cosmos was just a few 100,000 years old are leaving their imprints for us to observe. Finally, scientists can begin to answer the question, what did young galaxies look like? Galaxies have evolved from clusters of stars to the complex web of systems we see today, and this process is being seen by astronomers. As far as we can tell, the greatest structures in the universe today originated as star clusters, evolved into galaxies, formed clusters of galaxies, and ultimately coalesced into superclusters of galaxies. There was a lot of stardust gas and clumpy structures in the early galaxies. However, modern galaxies seem organized and tidy. When and how can tangled clusters of galaxies become neatly organized spirals and pinwheels? Gravity is the explanation. Galaxies are molded by gravity, and its effects determine their fate. At the center of most galaxies lies an unfathomably strong and destructive gravity source, and our own Milky Way has one hidden at its core. Over 12 billion years have passed since galaxies first appeared. These stellar conglomerations may take many forms, from spirals to giant spheres of stars, as far as we can tell. However, there is still a great deal we don't understand about galaxies. How did galaxies evolve into their present forms? Did spiral galaxies always have to be spirals? In all likelihood, the answer is not yes. Young galaxies are a mix of stars, gas, and dust. They are untidy and chaotic. They begin as chaotic formations like the Whirlpool galaxy, then over billions of years develop into more orderly forms, or the Milky Way itself. The Milky Way wasn't born from a single galaxy, but from a cluster of several. Our Milky Way originated as a collection of disparate formations, objects of varying sizes and shapes, that gradually merged to become the galaxy we see today. Gravity is what binds the various components together. Over time, it gradually draws stars closer. They pick up speed and flatten out into a disk shape. Massive spiral arms gather stardust and gas. This process was carried out countless times during the course of the cosmos. While visually distinct, these galaxies share the fact that they all seem to circle the same central object. For a long time, researchers pondered what might possibly alter a galaxy's behavior. As it turned out, it was a black hole. And not just any kind of black hole, a supermassive black hole. The discovery of extreme amounts of radiation coming from the centers of certain galaxies was the first indication of supermassive black holes. Black holes in these galaxies are eating their surroundings much like a giant Thanksgiving feast. The gas and stars are the supermassive black hole's dinner. Sometimes black holes consume their food so rapidly that they spew it out into space as beams of pure energy. They refer to it as a quasar. The presence of a quasar indicates the presence of a supermassive black hole at the center of the galaxy. However, what about the Milky Way? There's no quasar here. Does it rule out the existence of a supermassive black hole? So observing the motion of the stars is the key to finding the supermassive black hole in the heart of our Milky Way. Like the planets that circle the sun, the stars also move due of gravity. What we discovered was a bizarre and violent environment. At the center of our galaxy, everything is more extreme. Things move very quickly. The stars will be passing one another at high speeds. It is unlike any other place in the universe. The photographs of the stars in orbit showed a remarkable phenomenon. They had to have been traveling at 1,000,000 miles per hour or more. Only a gigantic black hole has the energy to toss large stars around like that. This curvature was the conclusive evidence for a supermassive black hole at the heart of our galaxy, as it is the black hole's gravity that drives the orbits of these stars. A massive black hole measuring 15 million miles wide sits at the heart of our Milky Way galaxy. In reality, the distance between Earth and the supermassive black hole in the heart of the Milky Way galaxy is 25,000 light-years. For the time being, Earth is secure. Although supermassive black holes are the source of enormous quantities of gravity, they are not strong enough to bind galaxies together. In reality, the rules of physics dictate that galaxies should accelerate away from one another. So what's stopping them? Because there's something stronger than a gigantic black hole waiting to be discovered. It is invisible and very difficult to detect. It's called dark matter, and it's everywhere. Supermassive black holes discovered by astronomers are found in the centers of galaxies, and are responsible for the rapid movement of stars in their vicinity. However, they are insufficient to hold together all of the stars in a vast galaxy. What then is it that keeps them together? It was a mystery until a maverick scientist proposed that something unknown was at action. Fritz Zwicky, a Swiss astronomer, pondered in the 1930s why galaxies clustered together. He reasoned that because they weren't producing enough gravity, they should be flying apart. However, the force of our own gravity was insufficient. Therefore, he deduced that it must be something that had never been discovered before, something that had never even been considered, and he called it dark matter. Fritz Zwicky irritated his fellow astronomers because he was so far ahead of his time. And this is a brilliant idea, but he was correct, you know. It's possible that individual galaxies are also held together by the mysterious substance that Zwicky dubbed dark matter. Galaxies rely on dark matter as a kind of protective framework that keeps them from collapsing and moving about. Now scientists have discovered that dark matter does more than just bind galaxies together. It may have also triggered their evolution. Scientists believe that after the Big Bang, dark matter started to cluster, and these dark matter clumps evolved into the galaxy's nucleus. However, the nature of dark matter is still a mystery to physicists. Weird things happen with dark matter since we don't know what it is. Obviously, it's not constructed from the same substance that humans are. You can't push against it, you can't feel it. However, it is likely everywhere. It's a ghostly substance that can go through you without registering your presence. Although our understanding of dark matter is limited, it seems to be abundant across the cosmos. That means there must be at least 6 times as much dark matter as regular matter, what humans are comprised of in the cosmos. And the way the cosmos seems to function depends on it. Observations of its effects on light have led to its recent indirect detection in deep space. Through a process known as gravitational lensing, it warps the light. The existence of dark matter may be tested using gravitational lensing. As a ray of light from a distant galaxy travels towards us, its course will be bent around a huge collection of dark matter due to the latter's greater gravitational attraction. Some distant galaxies indeed seem stretched and warped when seen via the Hubble telescope. The picture distortion is due to the presence of dark matter. We can determine the density of dark matter by carefully examining the forms and degrees of distortion of these galaxies. Now more than ever, the importance of dark matter to the cosmos is undeniable. It's what makes galaxies form and stops them from collapsing. Even though it's invisible and undetectable, dark matter rules the cosmos. These galaxies seem to be completely alone. It's true they are trillions of miles apart. But actually, they live in groups called clusters. And these clusters of galaxies are linked together in superclusters containing tens of thousands of galaxies. The Milky Way's place in the cosmos remains a mystery. If you look at the overall image, you'll see that our galaxy is associated with a smaller group of galaxies, including about 30 members in total, and that our galaxy and Andromeda are the 2 largest members of this group. Further observation reveals, however, that our galaxy is embedded inside the Virgo supercluster. Researchers are now making maps of galaxy clusters and superclusters to better understand the cosmos. Galaxies are the immense star empires. The shapes range from enormous balls to intricate spirals. The problem is that they are always evolving. When we stare out into the cosmos, it's easy to assume that our galaxy hasn't changed in eons. It's not. The Milky Way is a dynamic galaxy. Over cosmic eons, its basic nature has been changing. Galaxies don't only evolve, they move as well. And sometimes they run into each other. The 2 galaxies will merge over millions of years when they collide. This kind of collision occurs all the time in the cosmos. Our own Milky Way is no exception. We are on a collision course with the galaxy Andromeda. And that's terrible news for the Milky Way. At a speed of around 250,000 miles per hour, our Milky Way galaxy will collide with Andromeda in about 5 billion to 6 billion years It's all over for the Milky Way galaxy. If you could look out into space, you'd see the whole Andromeda galaxy hurtling toward us at a tremendous rate of speed. As the two galaxies interact, they both become more and more disturbed, and closer together. There will be a dance of death between the two galaxies. Whenever galaxies collide, they release clouds of gas and dust in all directions. As galaxies collide, their combined gravity rips stars from their orbits and launches them into the void. As we approach doomsday for the Milky Way galaxy, it would be spectacular. The two galaxies will ultimately pass through one another and merge into a single one. The Milky Way and Andromeda, as we know it, will cease to exist, and Milkomeda will be born, and it will look like a whole new galaxy. There's no escaping what's going to happen. The question is, what's it mean for planet Earth? We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy. Stars and planets will be pushed all over the place, so this may well be the end of planet Earth. Galaxies all over the universe will continue to collide, but this age of galactic cannibalism will eventually pass, because there is an even more destructive force in the universe, a force that nothing can stop. It will eventually tear the cosmos apart by stretching everything to the point that galaxies are pushed apart from one another. Researchers have identified a new cosmic power. It's called dark energy. Unlike dark matter, dark energy has the opposite effect. It pushes galaxies apart rather than bringing them together. Dark energy, which we've only discovered in the last decade, and which dominates the universe, is significantly more enigmatic. We don't have the slightest idea why it's there. What it's made from, we don't really know. We are aware of its presence, but beyond that, our understanding of it is limited. Dark energy is really weird. Things resist and are pushed away from one another, as if space itself contained tiny springs. In the far future, scientists predict that dark energy will triumph over dark matter in the cosmos. And with that triumph, galaxies will finally begin to drift apart. Galaxies will eventually die off due to dark energy. It will do this by accelerating the expansion of the universe, forcing all galaxies to recede farther and further away from us until they become invisible and travel faster than the speed of light. Therefore, everything else in the cosmos will vanish before our own eyes. The remainder of the cosmos won't vanish today or tomorrow, but it may after 1 trillion years. Galaxies will be left alone in the void. However, this will not occur for an extremely lengthy period. The cosmos is doing well right now, and galaxies are creating favorable circumstances for life to exist. Without galaxies, I wouldn't be here. You wouldn't be here. Maybe not even life itself would exist. This is fortunate for us. The only reason why life has evolved on Earth is because our minuscule solar system was formed in the correct region of the galaxy. If we were any closer to the center, well, we wouldn't be here. Life in the center of a galaxy may be extremely hazardous. In point of fact, the proximity of our solar system to the core of our galaxy would render it so radioactive that it would be impossible for life to continue in any form. Too far away from the center would be just as bad. Out there aren't as many stars. We might not exist at all. We are therefore, in a sense, in the Goldilocks zone of the galaxy, neither too close nor too far away, but just right. There may be millions of stars in the cosmic Goldilocks zone, where conditions are just suitable for life, according to scientists. Furthermore, if our galaxy can support life, then other galaxies should be able to as well. The cosmos is very large, and the really incredible part is that we continue to learn new things about it. Every time we believe we've figured out a solution to an issue, we uncover that it's really part of an even greater one. That's awesome. Our Milky Way galaxy and the galaxies beyond it are rife with mysteries and unanswered questions. Who would have guessed 20 years ago that we would be able to identify the black hole at the center of the galaxy. Who would have predicted 20 years ago that the astronomical community would accept the existence of dark matter and dark energy? We should be astonished to be alive at this particular moment in cosmic history, on this particular planet, on the fringes of this particular galaxy, with the ability to ponder questions and seek answers across the whole cosmos. Galaxies are born, they evolve, they collide, and they die. The Milky Way is a fortunate home for intelligent life. Our fate is intertwined with that of every galaxy. Ultimately, our fate rests in their hands, since they are the ones who created us and are shaping our identities. Imagine for a moment that 93 million miles away, a powerful force is brewing, a force so intense that it has the potential to disrupt your daily life in ways you wouldn't expect. I'm talking about our very own sun, currently experiencing one of the most turbulent and awe-inspiring phases of its life cycle, the solar maximum. Right now, the sun is buzzing with activity, and its effects are being felt across the universe and even here on Earth. Why should you care? You might wonder, what does this fiery giant have to do with me? Well, a lot more than you think. The sun's increased activity during this solar maximum doesn't just lead to beautiful auroras in the night sky. It can disrupt power grids, scramble your GPS, and interfere with radio communications. It's like an invisible storm raging across the cosmos, and it's influencing the technology we rely on every day. But to really grasp what's happening right now, we need to talk about the sun's 11-year cycle. Think of it as the sun's natural rhythm. It goes from quiet to chaotic, and back again over a period of 11 years. At the start of the cycle, things are calm. Fewer sunspots, fewer flares. But as we approach the solar maximum, all that changes. The sun becomes much more active, its surface crawling with sunspots, and bursts of energy explode in the form of solar flares. This is where we find ourselves now, right in the middle of this intense phase. Scientists from NASA and NOAA have confirmed that the sun is reaching its peak, and this solar maximum will continue for at least another year. So what does that mean for us? How does this massive ball of fire affect our modern world? And what can we expect as it continues to blaze with energy? Stay tuned as we dive into the fascinating world of the solar maximum, the science behind it, and why the sun is far more than just a bright light in the sky. Now let's really dig into what's happening during this solar maximum. What exactly is a solar maximum? Think of it as the sun's stormy season, but instead of rain and wind, the sun's magnetic field goes wild. During this phase, the sun's magnetic field becomes twisted and tangled, leading to the appearance of sunspots, those dark patches you might have seen in solar images. But don't be fooled by their appearance. These sunspots are cooler areas, but they are where all the solar action begins. When the sun's magnetic field lines cross or tangle too much, they snap, releasing massive bursts of energy called solar flares. These flares are so powerful they can shoot out waves of radiation and particles toward Earth at incredible speeds. And when those waves hit us, they can have a very real impact. How do scientists know this is happening? NASA and NOAA are constantly monitoring the sun with specialized satellites and observatories watching for these sunspots and solar flares. The latest data shows that we are smack in the middle of a solar maximum. Scientists measure the sun's activity by counting sunspots and tracking solar flare intensity. And right now, they're seeing an uptick in both. This heightened solar activity is all part of the sun's 11-year cycle, which shifts from quiet to chaotic. But don't worry, we're not talking about apocalyptic events. These are natural cycles that have been happening for millions of years, and they're crucial for understanding the sun's behavior and, by extension, the environment in space around Earth. What makes this solar maximum particularly interesting is that it's a little stronger than some scientists predicted. We're seeing more sunspots and stronger solar flares than expected, and that means the sun's magnetic field is even more twisted and dynamic than usual. But what does that mean for us? Let's talk about how this solar maximum affects you and me. When solar flares or coronal mass ejections, giant bubbles of solar plasma reach Earth, they can disturb our planet's magnetic field, creating geomagnetic storms. These storms can have a few different effects. In extreme cases, a powerful solar storm can overload power grids, leading to blackouts. Solar flares can mess with the electronics on satellites, causing communication and navigation issues. Think GPS not working or your phone signal suddenly dropping. On the bright side, these solar storms can also trigger stunning displays of auroras, those glowing, colorful lights in the sky, also known as the northern and southern lights. So while the solar maximum brings some risks, it also delivers one of nature's most beautiful shows. And who doesn't love the idea of gazing up at a brilliant aurora, knowing it's a direct result of our sun's activity? Now that we understand the solar maximum, let's zoom in on two key players in this cosmic drama: sunspots and solar flares. Sunspots are cooler areas on the sun's surface, but they're anything but calm. They're actually where all the action begins. Think of them as the sun's storm clouds. Sunspots form because the sun's magnetic field is all twisted up, and where these magnetic field lines get really tight and intense, sunspots appear. What's fascinating is that these sunspots can be enormous. Some of them are even larger than Earth. As they increase in number during a solar maximum, scientists keep a close eye on them because they tell us how turbulent the sun's magnetic activity is getting. Sunspots are also the birthplace of solar flares. Picture a rubber band stretched to its limit. Eventually it snaps. That's what happens with the sun's magnetic field around sunspots. When the tension gets too high, the magnetic lines suddenly realign, and boom, a solar flare is born. Solar flares release enormous amounts of energy, equivalent to billions of nuclear bombs exploding at once. When a solar flare happens, it sends out intense bursts of radiation. Most of this radiation doesn't reach the surface of the Earth, but it can seriously disrupt our atmosphere. These flares can mess with satellite communications, knock out GPS systems, and even disrupt high-frequency radio signals. Imagine you're driving, relying on your GPS to navigate a busy city, and suddenly, no signal. That's a minor example of what a solar flare can do. For instance, in 1972, a solar flare knocked out long-distance telephone communication across several US states. And while technology has advanced since then, we are even more dependent on satellites and electronics today, making us more vulnerable to these space weather events. Sometimes, along with solar flares, the sun also throws out huge clouds of plasma in what's known as a coronal mass ejection, or CME. These are the real heavy hitters of solar storms. If a CME is directed toward Earth, it can cause massive geomagnetic storms. When a CME reaches Earth, it can compress our planet's magnetic field and trigger geomagnetic storms. These storms can induce electric currents in power lines, potentially overloading transformers and causing widespread blackouts. One of the most famous examples is the 1989 Quebec blackout, where a geomagnetic storm caused a province-wide power outage. But CMEs don't just wreak havoc. They also create spectacular auroras. The particles from these solar storms interact with our atmosphere, lighting up the skies in vibrant greens, pinks, and purples. So while there's risk involved, there's also beauty in these cosmic phenomena. The more sunspots and solar flares we see, the more likely it is that one of these solar storms will hit Earth. That's why scientists are so interested in studying the solar maximum. They're not just observing for the sake of science. They're using this data to predict space weather and protect our technology. The better we understand these solar events, the better prepared we can be. Let's move beyond Earth for a moment and talk about space. During a solar maximum, the sun's increased activity doesn't just affect life down here. It poses a significant risk to astronauts and the technology we depend on in space. Imagine being an astronaut on the International Space Station ISS orbiting Earth as the sun throws out bursts of radiation. During a solar maximum, astronauts are at higher risk of exposure to dangerous levels of solar radiation. This can affect their health, causing radiation sickness, and even increase the risk of long-term problems like cancer. That's why space agencies like NASA have strict protocols during heightened solar activity. If a strong solar storm is on the way, astronauts might have to take shelter in specific areas of the ISS that are better shielded from radiation. Then we have satellites, those silent sentinels that orbit Earth, providing us with everything from GPS to satellite TV. During solar maximum solar flares and coronal mass ejections, CMEs can wreak havoc on these delicate instruments. You see, satellites are bombarded by charged particles from the sun, which can damage their electronics, causing them to malfunction or even fail altogether. One example of this happened in 1997, when a solar storm knocked out a major telecommunications satellite, causing issues with TV signals, credit card transactions, and even pagers back when we still used those. Today, we rely on satellites even more, and a similar event could have widespread consequences for communication and navigation systems. How do scientists protect against this? NASA, NOAA, and other space agencies monitor the sun's activity, closely tracking sunspots and solar flares in real time. They use this data to predict space weather and issue warnings when solar storms are coming. This allows engineers to put satellites in a kind of safe mode, where they limit non-essential functions to protect sensitive electronics from being fried by solar radiation. Engineers also build shields into satellites to protect them from these radiation blasts. It's like giving our tech in space a layer of cosmic armor. But even with these precautions, solar storms are unpredictable, and the most powerful ones can still cause damage. Let's bring it all together. We've seen how the sun, in its solar maximum, can cause a cosmic storm affecting life on Earth, and even beyond, from disrupting power grids to threatening astronauts. But it's not just about the risks. It's also about learning and preparing for the future. The solar maximum will continue for another year or so, giving us a unique opportunity to study the sun during one of its most dynamic phases. And as we prepare for future missions to the Moon, Mars, and beyond, learning about solar activity becomes even more crucial. The sun, once thought to be an unchanging ball of fire, is actually a living, breathing star with a profound impact on our lives. Remember, we're all connected to this massive star in ways both visible and invisible. Whether it's powering your GPS, dazzling you with northern lights, or sending a storm that shakes up space, the sun's cycles are a cosmic reminder of our place in the universe. Can science fiction become reality? This question isn't just for fans of novels or movies. It's one of humanity's greatest mysteries. The discovery of extraterrestrial life and possibly making first contact would undoubtedly rank as one of the most monumental scientific breakthroughs in history. Yet the universe seems to act like an enormous wall, putting up countless barriers between us and other potential civilizations. Despite these challenges, we continue to search for answers among the stars. Are we truly alone in the cosmos, or is intelligent life waiting somewhere out there, just beyond our reach? The Arecibo message. Our first attempt in 1974. Something incredible happened. At the Arecibo Observatory in Puerto Rico, we sent a powerful radio message deep into space. This wasn't just a casual hello, it was a carefully crafted message packed with information about Earth, our location, basic biology, and even the structure of our DNA. The message was aimed at a star cluster called M13, located about 25,000 light-years away. If there's intelligent life out there, this was our way of saying, "We're here. Are you?" It was humanity's first direct attempt to communicate with a possible alien civilization. But here's the catch: even traveling at the speed of light, that message won't reach its destination for another 25,000 years. And if anyone replies, well, we'll have to wait another 25,000 years to hear back. It's a bold move when you think about it. We're sending out a message with no guarantee that anyone is listening. But it raises the ultimate question: are we really alone in the universe? Is there life out there? So how likely is it that someone or something is out there waiting for our message? The answer seems obvious: yes. Life on Earth began almost as soon as our planet formed. If it could happen here, why not somewhere else? Astronomer Frank Drake tried to tackle this question with a groundbreaking approach. He created the Drake equation, a formula designed to estimate the number of intelligent civilizations in our galaxy. When the equation was first introduced, scientists projected that there could be about 10,000 civilizations capable of communication. Since then, our understanding of the universe has grown dramatically. For one, we've discovered exoplanets, planets orbiting stars outside our solar system. At last count, astronomers have confirmed over 5,500 exoplanets, and they believe that's just the tip of the iceberg. What's more, scientists now estimate there may be more planets than stars in the cosmos. If the universe is so good at making planets, it stands to reason that it might also create the conditions for life. Even if life is rare, the sheer size of the universe offers countless opportunities for it to exist. The odds seem to favor the idea that intelligent civilizations are out there somewhere. But here's the mystery: if there's so much potential for life, why haven't we found any evidence yet? The vastness of the cosmos. If the universe is brimming with possibilities for life, then why haven't we found anyone yet? One answer might lie in the sheer size of the cosmos. It's hard to wrap our heads around just how vast everything is. Take our own galaxy, the Milky Way. It's so big that even traveling at the speed of light, a signal sent from one end to the other would take 100,000 years to arrive. We're out here in the suburbs of the galaxy, about 75,000 light-years from its edge. That's a long way from any cosmic neighbors. Now think about the Arecibo message. After 45 years, it has only covered a fraction of the distance to its target. At this rate, communication with another civilization becomes a waiting game on a scale we can barely imagine. Even if there are thousands of intelligent civilizations in the galaxy, the distance between us might be so immense that we'll never hear from one another. The laws of physics don't make it easy. Nothing can travel faster than the speed of light. So no matter how advanced we become, those vast distances are a roadblock we can't get around. But that hasn't stopped us from trying. Projects like Breakthrough Listen are using the most advanced technology on Earth to scan the skies. With radio telescopes and optical sensors, they're focusing on the stars and galaxies closest to us, searching for any signs of intelligent life. So far, it's been quiet, like waiting for a call that never comes. But that doesn't mean no one's out there. It just means we're still looking. The patience of the search. Searching for extraterrestrial life is a bit like looking for a needle in a cosmic haystack. Imagine this: even if there are 10,000 intelligent civilizations in the galaxy, there are roughly 250 billion stars out there. That's like trying to find one specific house in a city of 25 million. It's an enormous challenge, and it's going to take time. Even if we do eventually hear something, there's another problem: time itself. Imagine a civilization sends us a signal, but by the time it reaches us, they're already gone. Civilizations rise and fall, and the timeline of the universe is so vast that we might simply be missing each other. Earth has been around for 4.5 billion years, but humans, we've only been here for about 300,000 years. In cosmic terms, we're late to the party. The universe is 13.8 billion years old, meaning other civilizations could have existed billions of years before us. They might have reached incredible technological heights, only to disappear long before we even began searching. But this doesn't mean we should give up. Our search is just getting started. Breakthrough, listen for instance, is focusing on the 1/700 stars nearest to us, using cutting-edge technology to catch even the faintest signal. If there's life out there, projects like these are our best hope of finding it. For now, though, we wait, and in the grand timeline of the universe, patience might be the most important tool we have. The Kardashev scale, measuring civilizations. If intelligent civilizations exist, how advanced could they be? To answer this, scientists use something called the Kardashev scale, which ranks civilizations based on their ability to harness energy. Type 1 civilizations can use all the energy available on their home planet. Type 2 civilizations can harness the energy of their entire solar system. Type 3 civilizations are the ultimate powerhouses capable of using energy from an entire galaxy. And where do we stand? Well, we're not even at Type 1 yet. Humanity is somewhere around Type 0.7, still learning how to fully utilize the energy resources of Earth. But the Kardashev scale offers a glimpse of what might be possible if a civilization survives long enough to keep advancing. Imagine a Type 2 civilization. They might build something like a Dyson sphere, a structure that surrounds a star and captures nearly all of its energy. First proposed by physicist Freeman Dyson, this concept represents technology so advanced it's almost hard to imagine. If such structures exist, they would block most of the star's light, leaving only faint traces of infrared radiation, something we could potentially detect. In 2015, NASA's Wide Field Infrared Survey explorer WISE scanned the skies looking at 100,000 galaxies for signs of these advanced civilizations. But they found nothing. Not a single confirmed Dyson sphere. Does this mean Type 2 or Type 3 civilizations don't exist? Not necessarily. They could be too far away, too rare, or using technology we can't even comprehend. The lack of evidence doesn't mean the universe isn't teeming with life. It just means we haven't found it yet. Are we late to the party? The universe is old, 13.8 billion years old, to be exact. Civilizations could have risen and fallen long before Earth even formed. It's humbling to think that while humans have been here for about 300,000 years, that's just a blink in the timeline of the cosmos. Some scientists believe this might explain why we haven't made contact yet. It's possible that intelligent civilizations existed billions of years ago, but are now long gone. Imagine a message finally reaching us from another world only for us to discover that the senders vanished ages ago. It's like trying to join a party, only to find out it ended before you even got the invitation. But there's another possibility. What if we're the early ones? Earth may seem ancient to us, but in the grand timeline of the universe, we could be among the first intelligent species to emerge. If that's true, it's not just about waiting for others to contact us. It's about deciding what kind of civilization we want to be. Right now, humanity is at a crossroads. We're building the tools to explore the cosmos, but we're still learning how to take care of our own planet. If we ever hope to reach the levels of a Type 1 or Type 2 civilization, we'll need to survive the challenges of today. Our search for extraterrestrial life is about more than just finding aliens. It's about understanding our place in the universe. Whether we're latecomers to the cosmic party or among the first civilizations to emerge, the quest itself is a testament to human curiosity and resilience. Projects like the Breakthrough Listen initiative remind us that even if the universe is vast and the odds seem impossible, we are determined to keep looking. Every discovery, from exoplanets to radio signals, brings us closer to answering the question, are we alone? But maybe the most important takeaway is this: the universe doesn't owe us answers. The search for intelligent life might take decades, centuries, or even longer. Yet by exploring the cosmos, we're not just searching for others, we're learning about ourselves. Humanity is still in its infancy on the cosmic scale, but we have the tools and the ambition to grow. One day we might become the advanced civilization others are searching for. Until then, we'll keep listening to the stars, sending out our messages, and dreaming of the day we finally hear something back. Some stars are so massive, so luminous, they could swallow our entire solar system and still have room to breathe. Tonight you'll drift past them, not as an observer, but as a traveler. These are the behemoths, cosmic titans that live fast, burn furiously, and explode with enough energy to shape galaxies. And somewhere in their death is the reason you exist. And some of these stars, they're colossal. If seen clearly, one would engulf Mercury, Venus, Earth, and even Mars. These are the titans you came to meet. Despite their grandeur, these giants are fleeting. They live fast and die spectacularly, returning their matter to the universe that gave birth to them. As you drift closer, you begin to understand they are not just fascinating, they are foundational. Without them, you wouldn't be here. Their collapse forged the elements in your bones, your blood, the air you breathe. You are quite literally made of star stuff. So before you settle in, if journeys like this mean something to you, consider liking the video and subscribing, but only if you genuinely enjoy this kind of voyage. And I'd love to know, where are you watching from? And what time is it right now? Now, dim the lights. Maybe turn on a fan for that soft hum, and let's begin tonight's journey. You start in a quiet corner of our galaxy, near the local neighborhood of stars. Through the lens of space, even nearby suns seem faint. Their light has traveled for years to reach you, moving at nearly 300,000 kilometers per second. Out here, distance is time. 1 year of light travel equals nearly 10 trillion kilometers. It's a number so large, it slips away from grasp. So when you gaze at Scuti, the giant star we'll meet tonight, you're seeing it not as it is, but as it was, almost 10,000 years ago. And when you arrive at its doorstep, what greets you isn't fire. It's haze, a deep red fog, like a slow breath, exhaled by the universe itself. The star is old, massive, a red supergiant that once blazed blue in its youth. Over millions of years, it swelled outward, its core still fusing elements in violent heat. Hydrogen to helium, helium to carbon, carbon to oxygen. Like layers in a cosmic oven, its surface isn't solid, but roils with convective gas. Bubbles the size of planets rise and fall. Like boiling water, the outer layers are barely held together. Gravity and radiation, locked in a fragile, flickering dance. Even from millions of kilometers away, the heat would unmake you. And yet, you feel calm, small, in the best possible way. Not diminished, but placed in scale. A quiet thought passes through. How many of these giants float in the Milky Way alone? Tens of thousands, maybe more, most hidden behind dust and silence. Even now, drifting near Scuti, you see the night isn't black, it's velvet, deep, laced with soft radiation, the afterglow of ancient energy. Cosmic microwave background, ionized hydrogen, light from galaxies too far to resolve. Some astronomers still debate whether Scuti is truly the largest. Stellar measurements are delicate. Dust mass loss and distance skew the numbers, but that's not what matters. What matters is this: you're floating beside a thing so vast, even your imagination struggles to grasp it. And this is only the beginning. Ahead, more giants await. You begin to understand how far and how bright these behemoths shine across interstellar space. You drift slowly as if weightless on a current of thought and photons. The distances between stars stretch like taffy pulled across eons. There are no hard lines in space, only gradients between heat and cold light and shadow time and timelessness. Light, the quiet courier of space, is your guide. It reveals not only where a star is, but when it was. This simple idea becomes profound out here. To look at the stars is to peer into the past. Every twinkle you remember seeing from Earth is ancient. Even the nearby Alpha Centauri system is more than 4 years gone by the time its light touches your eye. For behemoth stars, this becomes even more powerful. Their light can stretch across entire galaxies, even briefly outshining all the other stars combined. These are luminous giants, massive bodies whose brilliance is not merely for show, but a byproduct of immense energy and violent fusion. And yet, even the brightest among them are dwarfed by the scale of interstellar space. Light moves fast, but the cosmos expands faster still. You float past a point where the light from one star, one magnificent swollen supergiant, has been traveling for 10,000 years and is just now passing by your invisible shoulder. The brightness of a star isn't just about its actual power. It's about perspective, its luminosity, versus its apparent brightness. A nearby candle can outshine a distant bonfire. But astronomers have learned to disentangle this illusion using the inverse square law of light. Each doubling of distance makes the light appear 4 times dimmer. So when you see a star like R136A1 burning at its core with temperatures over 50,000 Kelvin, you know it must be truly luminous to appear as bright as it does from Earth. Another star, Deneb. A blue-white supergiant in Cygnus is so bright it rivals other nearby stars. Even though it's nearly 2,600 light-years away, its light left around the time ancient Mesopotamians were building ziggurats. And only now it reaches us, quietly, consistently. A reminder that space is not empty. It is full of stories told in photons. You imagine yourself traveling at the speed of light. Even then, you realize it would take years to traverse just this quiet arm of the galaxy, across the Milky Way over 100,000 years. And yet light makes this journey, every second, without fatigue. No vessel, no engine, just momentum and time. And as you float, you start to sense a subtle truth. That starlight is the language of the cosmos. Every wavelength carries a message, a temperature, a speed, a chemical signature. And like a quiet archivist, the universe records its story, in spectra. One such story lies ahead. You notice it even now before you reach it, a faint crimson halo on the edge of darkness. The telltale glow of hydrogen alpha emissions filtered through interstellar dust. It marks the domain of another giant. You slow your pace, not from fear but from reverence. Because the star ahead, Stephenson 218, exists at the very boundary of known stellar dimensions. Some models suggest its radius is over 2,100 times that of the Sun. If placed in our solar system, its edge would stretch past the orbit of Saturn. And yet, you could fly past it and never truly see it, because it is cloaked, hidden, a ghost in the haze. Before you approach your thoughts, linger on the scale of this moment. You've traveled dozens of light years already, maybe hundreds, and still, you've only met a few members of this rare family of giants. Most stars in the universe are small, dim, and long-lived, like red dwarfs quietly burning for trillions of years. But here you are among the loudest, shortest-lived fires, stars that shape galaxies, stars that will soon vanish, leaving only dust-heavy elements and gravity behind. There's a subtle ache in this realization. That brilliance doesn't last, that the most powerful lights fade fastest. And yet, that too is natural. That too is beautiful. Some astronomers believe the upper limit of stellar size is still not well understood. We can model fusion and gravitational balance, but turbulence, magnetic fields, and stellar winds complicate the math. Observations help, but stars like Stephenson 218 lie buried behind veils of interstellar gas, visible only in slivers of infrared and radio data. Some question its precise size. Some argue it could be a cluster, but for now, it holds a kind of quiet throne in our records. A record, not of ego but of scale. As you prepare to approach, the light grows redder, deeper. Dust scatters short wavelengths, letting only the longest, warmest reds pass through. It's like drifting into a sunset that never ends. And even now, space holds its silence. No roar of fusion, no flicker of noise, just starlight, stretching into forever. You encounter Scuti, an immense red supergiant near the edge of known stellar scale. You arrive without a sound, slipping into the quiet reach of Scuti's domain. There is no firm edge to cross, only a gradual swelling of light and warmth, thick as breath. You hover now near one of the largest stars ever measured by volume, a red supergiant residing in the constellation Scutum, about 9,500 light-years from Earth. The star is not bright in the visible sense. Its energy is stretched and spread, softened by the sheer distance, and by the dust that floats between galaxies like fine smoke. What you see is not blinding, but warm. It glows in the deep red and infrared parts of the spectrum, casting a long, lazy light across the emptiness. Scuti is a strange place to imagine. A single object, and yet its surface would engulf the orbits of Mercury, Venus, Earth, and Mars. Light takes more than 7 hours just to travel from one side of it to the other. And yet it is not a solid thing, not even a clearly defined one. Its edges blur into the vacuum. Its atmosphere is a dance of heated gas, always rising, falling, and leaking away into space. Inside the vast convective layers of this star, pressure and temperature are constantly fighting gravity's slow pull. The outer layers swell because the radiation generated deep in the core is strong enough to push them outward. And in doing so, the star becomes fragile, unstable. Its surface is not uniform, but pocked with great cells of gas. Some astronomers believe a single one of these bubbles convective cells can be larger than Earth's entire orbit. At the center of this expanding colossus, fusion still occurs. Hydrogen has long been depleted, and helium is now fusing into heavier elements, carbon, oxygen, magnesium. This is a critical phase. The star is nearing its end. Once the core becomes too heavy to resist collapse, iron will form, and iron is the great boundary in stellar physics. Fusion of iron doesn't release energy, it absorbs it. When that moment comes, the balance shatters, and the star will implode. But that is still in the future. For now, Scuti pulses slowly, like a cosmic heartbeat. It is classified as a pulsating variable star, its brightness shifting as its outer layers expand and contract. This breathing cycle is slow, months long, and gives the star its rhythm, like the tide. From your vantage point, you observe another peculiarity. Scuti is losing mass. Its outer layers drift away, carried off by stellar winds, streams of particles blown by radiation pressure. Over time, this process peels the star apart. It's one of the reasons astronomers debate its actual size. Because the outer envelope is so diffuse, it's hard to say where the star truly ends. You reflect for a moment on how little of this was known just decades ago. In the 20th century, red supergiants were assumed to be rare, mysterious anomalies. Only with the rise of space telescopes and precise spectroscopic methods did we begin to map their true dimensions. And even now, some data is debated. Distance estimates, mass loss rates, temperature fluctuations. But uncertainty doesn't dim the wonder, it expands it. Some researchers propose that Scuti may shrink as it evolves, its mass loss and internal changes gradually collapsing it. into a hotter, smaller star before the final supernova. Others believe it may be on the brink already, that its next contraction could be the last. The supernova of a star like this would not just be bright. It would be transformative, a release of energy so vast it could outshine an entire galaxy for weeks. Neutrinos would flood space. Elements like gold, platinum, and uranium would be born in that furnace. This is cosmic alchemy, stars turning themselves inside out to seed the universe with complexity. But tonight, that moment is not here yet. Tonight you float beside a star so large, your mind falters at the scale. The texture of it, the slowness of its surface, the quiet distance of its core. You feel as though you are orbiting a whole world, not a single star. And still, even in this enormity, Scuti is not alone. Other giants await, some even larger, some far more massive. You begin to pull away, your thoughts still trailing behind. The red light lingers in your vision, like the afterglow of a dream. Ahead, space is darker again, but not empty. In the far silence, another giant pulses. This one, less known, more obscure, but perhaps even larger. Its name is whispered among catalogs and in quiet debates. Stevenson 218. You turn toward it, letting the light of Scuti fade gently behind you, and begin the slow glide, deeper into the realm of hypergiants. You learn why some stars are larger, others heavier, and how this affects their fate. As you drift onward, the red glow of Scuti dissolves behind you, like a sunset slipping below the edge of time. Ahead, space stretches wide and cool, a canvas of subtle light and gravitational tension. You move through stillness, but the physics beneath that stillness hums with complexity. Out here, size is not always what it seems. One star might swell to the edge of Saturn's orbit, yet possess only a fraction of the mass of another, smaller, hotter star. In astronomy, the distinction between volume and mass becomes crucial. You let your thoughts wander through this quiet paradox. Scuti, for example, is enormous in size, its radius vast, but its mass is relatively modest among giants, somewhere between 7 and 10 times that of our Sun. Compare that to a star like R136A1, which you will soon meet. That one is far smaller in diameter, but could contain nearly 200 or even 300 solar masses. It blazes with intensity, not through sheer size, but by its unimaginable density and fusion rate. Why is that? You consider the balance at the heart of every star, the push and pull of gravity and pressure. A massive star's gravity pulls everything inward, while fusion at the core pushes outward, releasing radiation. This balance defines the star's shape, size, temperature, and lifespan. The more massive a star is, the greater the pressure at its core. To maintain equilibrium, it must fuse elements more rapidly. That intense activity makes it brighter, but it also shortens its life. A giant like R136A1 might burn through its fuel in just a few million years. Meanwhile, a smaller star can shine calmly for tens or even hundreds of billions. Yet not all massive stars are large in radius. Many, like blue giants and Wolf-Rayet stars, are compact and hot. Their outer layers are stripped or compressed. Some, despite burning brightly, are barely 10 times larger than our Sun by radius. Nothing like the sprawling atmosphere of a red hypergiant. It's like comparing a bonfire to a smoldering ember the size of a mountain. Both burn, both glow, but one is intense, short-lived, the other diffuse and slow. This tension shapes every step of a star's life. Mass is also destiny. A star's mass determines what it becomes when it dies. If it begins with under 8 solar masses, it might swell into a red giant, and then settle quietly as a white dwarf, cooling slowly, over trillions of years. But if it starts with over 20 or 30 or more, its end is cataclysmic. A supernova, a neutron star, a black hole. There are thresholds, and you pass them silently as you drift. Somewhere behind you lies the boundary between stars that end quietly and those that collapse with violence. Somewhere ahead lies the limit where even neutron stars can't survive their own mass, and space folds inward. Some scientists propose more exotic ends, quark stars, for instance, hypothetical objects denser than neutron stars, but not quite black holes. In these stars, neutrons are squeezed so tightly that their constituent quarks may separate, forming a sea of strange matter. No such object has been confirmed yet, but the physics doesn't rule them out. Somewhere in the deep silence, perhaps one already exists. Back in your current path, mass continues to guide the stars you approach. The next behemoth, Stephenson 218, is an oddity. If estimates hold true, its volume exceeds even UY Scutis, and yet its mass, while substantial, is likely under 40 solar masses. It is wide, but not wildly heavy. A reminder that size does not equal strength. This behemoth likely belongs to a stellar association, a loose group of red supergiants known as Stephenson 2 or ST2, located around 19,000 light-years from Earth. The entire region glows in infrared, partially hidden behind a thick layer of interstellar dust. To see it, astronomers peer through long wavelengths, watching for thermal traces that shine. Like heat seen through fog, you reflect on how much of the universe is invisible, not because it's hidden maliciously, but because your human eyes are tuned to such a narrow band of light. Like listening to a song and hearing only one instrument. Fortunately, your thoughts have no such limits here. You float through X-ray bursts and infrared ribbons, through gravity waves and magnetic storms. Each layer of the universe adds another brushstroke to the vast, silent portrait. And as the shape of Stephenson 218 rises before you, still distant, still only a ghostly glow in the haze, you consider the quiet truth that space teaches best. That scale is not always power, that the universe is not arranged by what impresses the eye, but by what holds its balance. You drift slower now, as if nearing the edge of something sacred. You've learned how stars wear their size and mass like masks, some bright and dense, some vast and fading, and ahead, the deepest mask yet awaits. You approach a veiled red hypergiant, cloaked in interstellar dust, barely visible yet vast beyond measure. You pass through the last of the open void, entering a field of mottled shadows. The light here is soft, not because it isn't present, but because it is scattered and filtered by fine grains of interstellar dust. This is the domain of Stephenson 218, a red hypergiant so immense it defies simple comparison. Its true nature is shrouded, not only in distance but in uncertainty. Even today, it exists in our data more as a probability than a fully resolved object. The veil around it is literal, thick with carbon-rich dust and cool gas, and figurative, in the sense that many of its measurements are inferred from indirect observations. Still, the picture that emerges is staggering. The star lies approximately 19,500 light-years from Earth, in the constellation Scutum, nestled within a massive cluster known as Stephenson 2, a cradle of red supergiants. But Stephenson 218 is not simply one of many. It may be the largest of all, with a radius potentially exceeding 2,100 times that of our Sun. To put that in perspective, if you replaced the Sun with Stephenson 218, its photosphere would reach well past Saturn, and possibly graze the orbit of Uranus. You float slowly towards this diffuse colossus, and even now, you can't clearly define its surface. It is more atmosphere than object, more presence than point. Its outer layers are extremely tenuous, more like a fog than a skin. They drift, ripple, and escape into space. The density is so low, you could pass through the outer half of the star without ever feeling resistance, without even sensing that you were inside something at all. And yet, you drift through its outer envelope, immersed in a slow, churning sea of heated gas. Here, temperatures are relatively cool, around 3,000 Kelvin, and the pressure is low, But deeper in the story changes. The further you go, the more intense the heat, the more violent the motion. Turbulence rises. The fusion furnace stirs. Stevenson 218 is thought to be near the end of its life. Like UI Scuti, it has exhausted the hydrogen in its core and is fusing heavier elements in successive shells. Each fusion layer is like a nesting doll. Hydrogen, helium, carbon, oxygen, each deeper, hotter, and shorter-lived. Eventually, as with all massive stars, it will build up an iron core, and when that happens, gravity will win. In a fraction of a second, the balance will collapse, the core will implode, and the outer layers will rebound in a supernova, an explosion that will send shockwaves through the surrounding dust and gas, igniting new stars in its wake. It is the ultimate punctuation mark to a stellar life, but sometimes something even more exotic occurs. If the collapsing core is massive enough, the pressure can go beyond neutron degeneracy, the point where even neutrons resist compression. Gravity wins entirely, space folds in on itself, and the result is a black hole, an object so dense, not even light can escape. It is the final victory of gravity, the quietest and most complete. You float away from this imagined core, back toward the outer layers. Here the gases are lighter, more diffuse. Solar winds blow steadily outward. In massive stars, these winds are intense, stripping away mass at phenomenal rates. Over millions of years, a star might lose half its mass or more before it ever explodes. In lower mass stars like our Sun, fusion will never reach iron. It will stop at helium and carbon, eventually ejecting the outer layers in a soft, glowing cloud, a planetary nebula, and leaving behind a white dwarf, a dense cinder slowly cooling in space. The diversity of stellar fates all stems from this balance, how long fusion holds gravity at bay. And yet, you realize, no star lasts forever. Fusion is a delay, not a solution, a beautiful pause in the collapse that shapes all matter. And without it, there would be no light, no warmth, no planets, no life. In this moment, you feel the deep humility of that truth. Everything you are, all your atoms, all your breath, was once held inside a star's fusion engine, cooked, balanced, released, and given to the galaxy. Somewhere, a new star is forming. Somewhere else, another is fading. And you are exactly where you are meant to be, between them, resting in the pause, the echo, the space between pulses. May the silence of the cosmos cradle you. May the memory of the stars wrap you, and may the slow rhythm of drifting carry you into deep, unbroken sleep. Good night, traveler. Sleep well. Sleep wide. A star that's died, yet its power makes the universe tremble. Neutron stars, where matter is crushed to the extreme and the impossible becomes reality. Imagine staring into a cosmic void where a faint rhythmic pulse of light flickers like a heartbeat from an unseen star. What could forge such a relentless, radiant pulse, defying the silence of space? Welcome to the enigma of neutron stars, the pulsing hearts of the cosmos, where the ashes of colossal stars beat with a ferocity that reshapes our understanding of reality. These celestial relics born from cataclysmic explosions pack the mass of our sun into a sphere no wider than a city, spinning with a rhythm that echoes across light years. Far beyond what school textbooks taught, neutron stars challenge our grasp of physics, time, and existence itself, inviting us to peer into a universe both alien and awe-inspiring. Neutron stars are not just astronomical curiosities. They are cosmic laboratories where the laws of nature are stretched to their limits. Picture the heart of a supernova, where a dying star collapses, crushing its core into a dense, spinning orb that pulses with energy. This is no ordinary star, but a neutron star, a celestial marvel with a density so extreme that a single teaspoon of its material would weigh as much as Mount Everest. Its surface, smoother than glass, hides a core where matter may dissolve into strange, exotic forms. These stars don't merely shine. They broadcast their presence through beams of radiation, like a lighthouse sweeping the cosmos detected here on Earth as rhythmic pulses. Why do these pulses captivate us? Because they whisper secrets of the universe's most extreme conditions, encoded in a heartbeat that has traveled millions of years to reach our telescopes. This journey into neutron stars is a voyage through time and thought, one that will unravel mysteries school never touched. We'll begin by tracing the historical quest to understand these cosmic hearts, from ancient stargazers who glimpsed their explosive births to the scientists who decoded their rhythmic signals. Then we'll dive into the science of their extraordinary nature, how their immense gravity warps time, how their magnetic fields rival 1 trillion refrigerator magnets, and how they forge the gold in your jewelry. We'll explore modern discoveries from waves rippling through space-time to theories of alien matter lurking in their cores. Finally, we'll reflect on what these pulsing hearts reveal about our place in the vast interconnected cosmos. The neutron star's heartbeat is more than a signal. It's a mirror reflecting the universe's deepest truths. But why should we care about a star so distant, so strange? Neutron stars are not just relics. They are keys to unlocking questions that haunt us. How do stars die, and what do their deaths create? Can matter exist in forms we can't imagine? Might these cosmic hearts hold clues to the universe's origin, or its ultimate fate? As we stand on Earth, gazing at their faint pulses, we're not just observing. We're connecting with a force that shapes reality itself. The neutron star's pulse is a call to wonder, a reminder that the universe is alive with mysteries waiting to be explored. So let's follow this heartbeat, this radiant rhythm, and discover what lies beyond the lessons of school, deep within the pulsing heart of the cosmos. Long before telescopes pierced the heavens, ancient stargazers stood beneath a glittering sky, their eyes catching fleeting bursts of light from distant cataclysms. Could they have imagined that these fiery spectacles were the birth cries of neutron stars, the pulsing hearts of the cosmos? Thousands of years ago, in 1054, Chinese astronomers recorded a guest star blazing in the constellation Taurus, so bright it shone in daylight for weeks. Unknown to them, this was the Crab Nebula's supernova, a stellar explosion forging a neutron star whose heartbeat we still detect today. This cosmic pulse, a rhythm of radiant energy, has echoed through history, guiding curious minds to unravel a mystery schoolbooks barely touched. Let's journey through time tracing how humanity first heard the universe's pulse and began to understand its profound significance. In the 18th century, as astronomers mapped the stars, an English cleric named John Michel pondered a radical idea. What if a star's gravity was so immense that even light couldn't escape? His dark stars were a faint whisper of neutron stars too strange for his era to grasp. Fast forward to the 1930s, when Fritz Zwicky and Walter Baade, gazing at the cosmos, proposed that supernovae left behind dense cores. They called these neutron stars imagining a stellar corpse where matter was crushed into a near-infinite density. Their vision was like tuning a radio to catch the faint pulse of a cosmic heart, a signal too weak for the technology of their time. Yet their bold hypothesis set the stage for a discovery that would shake the foundations of astronomy. In 1967, a young graduate student, Jocelyn Bell Burnell, sat hunched over a radio telescope in Cambridge, England, sifting through reams of data. Amid the static, she noticed a peculiar regular blip every 1.33 seconds, as precise as a metronome. At first, her team dubbed it LGM-1, half joking that it might be a signal from little green men. But this was no alien broadcast. It was the pulse of a neutron star, a pulsar spinning furiously and beaming radio waves like a cosmic lighthouse. Bell Burnell's discovery was a triumph, revealing the neutron star's heartbeat to the world. The Crab pulsar, that ancient guest star of 1054, was among the first confirmed its rapid pulse, a testament to a star's violent end. Her work, though initially overlooked for a Nobel Prize, ignited a new era of cosmic exploration. These historical milestones, from ancient skywatchers to Bell Burnell's breakthrough, are like reflections in the cosmic mirror, each catching a glimpse of the neutron star's pulsing heart. They show humanity's relentless drive to decode the universe's signals, even when the tools were crude or the ideas outlandish. Michel's dark stars, Zwicky's dense cores, and Bell Burnell's blips were steps toward understanding a celestial enigma. Neutron stars, with their relentless rhythms, weren't just theoretical curiosities. They were real, their pulses a drumbeat echoing across the cosmos. As we move forward, we'll delve into the science behind these extraordinary objects, exploring how their heartbeat shapes the universe and what secrets it holds for us today. Picture a city-sized sphere spinning hundreds of times per second, its surface pulsing like the relentless beat of a cosmic heart. How can a neutron star, this pulsing heart of the cosmos, defy our everyday understanding of matter and time? These stellar remnants are not just dead stars. They are extreme laboratories where gravity, magnetism, and quantum forces collide in ways schoolbooks never dared to explore. Born from the fiery collapse of massive stars, neutron stars pack the sun's mass into a ball just 20 kilometers wide, creating densities so immense that a single sugar cube of their material would outweigh Earth's entire population. Let's unravel the science behind their extraordinary nature, from their crushing gravity to their role as cosmic alchemists forging the universe's heaviest elements. Imagine squeezing an ocean liner into a thimble that's the density of a neutron star. Its core, crushed by unimaginable pressure, may transform into exotic matter, perhaps a soup of quarks, unbound from normal atoms. This density warps space-time, bending light and slowing time itself. If you stood on a neutron star's surface, an impossible feat, your watch would tick slower than on Earth, a quirk of Einstein's relativity called time dilation. A minute there might feel like hours to a distant observer, as if the cosmic heart's pulse stretches the fabric of reality. This gravity is so fierce that mountains on a neutron star's surface, smoother than a billiard ball, are mere millimeters tall, flattened by the star's own weight. Yet this compact orb spins with dizzying speed, some pulsars whirling 700 times per second, faster than a kitchen blender, sending beams of radiation sweeping across space like a lighthouse's glow. These beams are powered by magnetic fields 1 trillion times stronger than Earth's fields, so intense they could rip apart a spaceship. When a neutron star's magnetic poles misalign with its spin, it emits radio waves, X-rays, or gamma rays, creating the pulses Jocelyn Bell Burnell detected. These pulsars are cosmic clocks, their beats so precise they rival atomic clocks, allowing astronomers to map the galaxy or test relativity. But neutron stars do more than pulse. They forge elements like gold and silver. During a supernova, rapid neutron capture creates heavy elements, and when two neutron stars collide, as seen in 2017's gravitational wave event, they spew these treasures into space. Picture the cosmic heart pumping, not blood, but the raw materials of planets and jewelry, a celestial forge shaping the universe's wealth. Beneath their surface, neutron stars hide mysteries. Their cores may host strange states of matter, like quark-gluon plasma, where protons and neutrons dissolve. Some theories suggest superfluids flow without friction, creating a frictionless dance within the star's heart. These conditions push physics to its limits, challenging our understanding of quantum mechanics. Neutron stars are also cosmic dynamos, their spins generating energy that outshines the sun for millennia. As we'll see next, modern discoveries are peeling back these layers, revealing how these pulsing hearts ripple space-time and hint at the universe's deepest secrets, all encoded in their relentless, radiant beat. What secrets does the pulsing heart of the cosmos whisper to us today as its radiant beats ripple through modern telescopes? Neutron stars, those city-sized relics of stellar explosions, are no longer just distant curiosities. They're cosmic beacons, illuminating the universe's deepest mysteries. In recent years, astronomers have caught their pulses in unprecedented detail, from gravitational waves born of their collisions to strange matter lurking in their cores. These discoveries, far beyond schoolroom lessons, reveal neutron stars as keys to understanding matter spacetime and even our technological future. Let's explore how the relentless heartbeat of these stars echoes through cutting-edge science, reshaping our view of the cosmos and sparking questions about what lies ahead. In 2017, a cosmic symphony reached Earth, detected by the Laser Interferometer Gravitational Wave Observatory, or LIGO. Two neutron stars locked in a death spiral collided 130 million light-years away, sending ripples through space-time. This event, named GW170817, was a milestone confirming that neutron star mergers forge heavy elements like gold and uranium as their pulsing hearts pump out a cosmic furnace. Telescopes caught the afterglow, a dazzling burst of light, proving these collisions light up the universe. Unlike black holes, neutron stars leave visible scars, their radiant pulses offering a window into gravity's extreme dance. This discovery linked the cosmic heart's beat to the creation of the very atoms in our world, suggesting that the jewelry on your finger owes its existence to such cataclysmic embraces. But what lies within a neutron star's core? Modern theories propose exotic states of matter, like quark-gluon plasma, where protons and neutrons dissolve into a primordial soup. Imagine the cosmic heart compressing matter so fiercely that it mimics the universe's state just after the Big Bang. Experiments like those at CERN's Large Hadron Collider aim to replicate these conditions, but neutron stars are natural laboratories, their pulses encoding clues about physics beyond our reach. Some suggest superfluids swirl in their cores, flowing without friction, while others hypothesize strange quark matter, a stable state denser than nuclear matter. These ideas push quantum mechanics to its limits, with each pulse of the cosmic heart offering a testbed for theories that could rewrite our understanding of reality. Neutron stars also inspire technological dreams. Their precise pulses, rivaling atomic clocks, could guide interstellar navigation, acting as cosmic lighthouses for future spacecraft. Magnetar's neutron stars with ultra-strong magnetic fields hint at energy sources dwarfing nuclear power, sparking ideas for harnessing their radiant energy. Philosophically, neutron stars challenge us if their cores hold alien matter. What does this mean for our place in the cosmos? Are we like their pulses, fleeting signals in an infinite universe?